Okay, let's get into this. So I'm gonna give a brief update on the quantum marketplace, give an overview of the trends in Quantum 2.0. We're going to have a very exciting lineup today, and then we're going to have a roundtable discussion, and then as John mentioned, we have a happy hour coming up, but we also have some upcoming quantum marketplaces that I want to talk about. Okay, so what is the quantum marketplace? Well, it's a platform to raise brand awareness and facilitates collaboration, deals partnership among the membership of QED-C. We've actually built out a directory on the QED-C homepage of all the companies, what they do, and a little icon there to the right of them for the ones that have participated and have a video from one of our video events that actually ends up on YouTube later so you can watch it later. This is our YouTube channel. All you have to do is type in Quantum Marketplace in Google. It takes you right there. So today we're going to have Coherent, NKT, Toptica, Vescent, Freedom Photonics, Infleqtion, and Riverlane. This whole session is being recorded. It will be on YouTube later after it's professionally edited. What is Quantum 2.0? Well, I think we first need to answer what is Quantum 1.0, and we've been living with the benefits of that for a long time, such as lasers, transistors, semiconductors, MRI scanners. And what is Quantum 2.0? Well, this is really enabling using much deeper levels of quantum to do quantum computing, quantum networking, quantum sensing, and quantum timing. This is, of course, not an exhaustive definition, but it's just to give you an impression of what this is about. So I thought today, since we had a marketplace, sort of market sizing session this morning, I thought, well, why don't we talk about money, right? So there's really three funding sources the way we see it. There's public funding, there's strategic funding, and there's sort of private professional funding. And we don't have time to go through all of this here, but I just want to give the impression here that, a lot of the money that's been flowing, public, strategic, and private, has been in quantum computing. Some of these other technologies have less funding, they need more funding, but I think it's just something to keep in mind. And also the two, the one on the left and the one in the middle, the funding continues. It's very strong. In fact, it's getting stronger. The column on the right is very opportunistic. There's still private investors that are interested, but they might be a little skeptical, but there's still enough interest. So, show me the money, right? Jerry Maguire. So this is a publicly available document from QRECA. This is, you may have seen data like this before, but they're claiming as of 2/23, there's been up to $33 billion invested in total by country. I put this together because, there's many Fortune 500 companies or Fortune 1000 companies involved in quantum. But these companies all have very varying degrees of efforts in quantum. They're doing quantum computing, they're doing various aspects, they're investing in some startups. They're companies to watch. And this is this is private funding. This is recent data from Alex and Evan at the Quantum Insider. And what I find noteworthy here is 2022, they say still, even though there was some skepticism if there was a little bit less funding, but it's still $2 billion. That's significant, right? So for today, Coherent, NKT, Toptica, Vescent, and Freedom, they all make lasers, right? But then Toptica and Vescent also make frequency combs. Freedom Photonics, they also make PICs. Infleqtion makes physics packages, and Riverlane does control and error correction. And these are all fundamental building blocks. It's not an exhaustive list, but these are all fundamental building blocks that are incredibly valuable and needed, or otherwise we're not going to commercialize certain aspects of quantum. Okay. So with that, I want to introduce our lineup today. So I mentioned Coherent. We have Marco, who's the Director of Marketing. We have Sasha, who's Sasha, who is the head of sales or VP of sales at NKT. We have Mark Tolbert, who's the CEO of the US entity at Toptica. We have Scott Davis, who's CEO of Vescent. We have Gordon Morrison, VP of engineering from Freedom Photonics. We have Chris Wood, CTO of Infleqtion, i.e. Cold Quanta. And we have Lunia Muk from Riverlane. And with that, I'd like to welcome Marco to the stage.
Thank you very much for the introduction, Mark, and good afternoon to all of you. So I'm Marco Rigoni with Coherent. I would like to start my presentation giving you a little flavor of Coherent Corporation, or the new Coherent Corporation, which is the result of 2.6 acquisition of Coherent Inc. At this moment, Coherent Corporation has 28,000 employees in many parts of the world. We have also basically, we are divided in 3 segments: in networking, materials, and laser sources. Our participation to the quantum market is historically connected to laser sources, and you see on the back a few examples of that. We made the lasers, the titanium sapphire and dye laser that powered the first experiment in cold atoms. We make very narrow linewidth laser used for optical trapping, and we make modular lasers that are used to address certain systems like Ytterbium ion platform. We also make VCSEL that are used actually in the CSAC, to give an idea. Now, what I want to show now is something that we are developing, and we had as a technology, proprietary technology, for a number of years. And I want to focus on 2 aspects here. The first one is what we call optically pumped semiconductor platforms. And you see here a couple of examples of the coverage. This is a technology that allows to cover by design a broad number of wavelengths by designing the semiconductor chip. And you see a flavor of that behind me with the coverage of this product in terms of infrared and visible wavelengths. Now, the beauty of this platform is that it can be expanded by tailoring different types of semiconductor platforms. And you see here an example of how we are going to expand the range of wavelengths available and also the relative power level. So this provides a step up in terms of power and wavelength coverage. The second aspect is that the combination of Coherent Inc. and 2.6 Corporation offers an incredibly broad spectrum of semiconductor laser technology. You see here some examples: tapered amplifiers, narrow linewidth diodes, narrow linewidth and linewidth narrowing devices, and a variety of processes to build these type of structures in a variety of materials. So just want to give a flavor of the first technology I mentioned, which is the optically pumped semiconductor laser. This is actually not a product. It's something that we demonstrated and we published at Photonics West of last year. It's a 15-watt device operating as a laser guide star at a wavelength of 589 nanometers. You see how compact it is, the size of a shoebox, and with a line width of 18 megahertz, without any effort on our part to narrow the line width. So it was just a very first step. So what excites us as a company looking forward? Our observation is that there is a wide number of atomic systems. If you look, for example, at schemes of atoms and ions used for quantum computing, and this is too much. There is a need for some pruning, and some pruning of the number of systems and the number of required wavelength also will result in a cost reduction, in a better standardization, and also in a higher level of reliability and consistency. At least this is our assumption. And also, this means that it will favor actually wider adoptions in the photonic industry. So what is at this point, what excites us, what we would like to do moving forward? We know that we master compelling material platforms like the one that I showed you before. Also, we will expand the platforms and the range of wavelengths and power available as the ecosystems matures with respect to the large number of systems that are proposed at this point. And last but not least, we also look for partnership and synergies in some aspect where we think that it would be beneficial for us and also our partner. A couple of examples I want to give is line width management to produce extremely narrow line width laser, and also on the side of photonics integration. where currently we are not a player in this industry. And with this, I just end my presentation, maybe with some time left even, and I thank you very much.
Good afternoon, everyone in the audience. It's a pleasure to see you after 3 years being back here in town. My name is Sasha from NKT Photonics, and I'm glad to talk to you about fiber lasers for Quantum 2.0. We at NKT Photonics are a Danish, headquartered fiber and fiber laser manufacturer, around about 450 people, with a dedicated focus on fiber technologies to enable the transformation from a quantum research market to an industrial market. Soon we are going to become a part of Hamamatsu Photonics, and we're truly proud and humble about this great opportunity and the future that brings for us. To give you a short introduction into what are we doing, we have today 4 primary markets we're working on. We're working in medical and life sciences, we're working in industrial, we're working in quantum and nanotechnologies, and we're working in what we call aerospace and defense. And the products we're using for these markets are distributed across our supercontinuum white light fiber lasers, our ultra-fast fiber lasers, our single-frequency distributed feedback fiber lasers, and last but not least, our proprietary microstructured photonic crystal fibers. The focus of this talk today is on our single-frequency fiber lasers within the quantum space. And I've decided to do a high-level overview for you. We can talk details in all the details afterwards. Since you're all here, you might all know that the quantum research market is actually transforming from research in the lab to an industrial deployment. And we can see that technologies like external cavity diode lasers, tapered amplifiers, Ti-sapphire lasers have, over more than 2 decades, enabled fundamental research on extremely exciting levels, great breakthroughs. But to transform all this to the next level, it needs more. So far, the focus has been on laser requirements like line width, properties like noise, as well as a variety of wavelengths. To make this transformation, we need more. And the more is literally based on what we hear from our partners and customers, the scalability and power to go from a few hundred qubits to thousands or to a million of qubits. And that goes through power scalability. The same goes into reliability, to have a predicted cost of ownership and lifetimes or reliabilities in the thousands of hours. And last but not least, for us laser manufacturers, the responsibility to scale the output of our production sites to scale with the needs in the market, so the scalability of the technologies. Our fiber lasers cover exactly these categories. And to show you a short introduction of what we are doing, I would like to use this for you. Everything starts for us with a DFB fiber laser, which emits light at 1 micron, at 1.5 or at 2 micron, with ultra narrow line width, ultra low phase noise, so a very stable laser intrinsically as it is. We're taking, with booster amplification, the next stage and scale the power up to 15 watt levels, while maintaining the purity and the pristine line of the fiber laser in itself. From there, we are using industrial conversion stages and convert the light into the proper colors needed to hit the atomic species of relevance. And last but not least, we're using our microstructured single-mode fibers to guide the light from the light source to the point of the experiment or to the point of the chip where it's needed. And that means we can deliver the light and enable flexible routing or rack mountability. So it creates space. When I'm talking about atomic species of choice today, we are focusing at NKT on 4 specific atomic species. It is primarily rubidium, strontium, barium, and ytterbium. And with this graph, I just would like to give a flavor of what has been achieved so far and what is going to happen in the future. Watt level in the UV, and up to 10 watt in the red part of the spectrum. So power scalability at its best through fiber amplification. And with this, thank you so much. Solutions for innovators, innovations like you probably, in the fiber space. Thank you.
Good afternoon, everybody. Thanks to SPIE and QED-C, and of course, Mr. Mark Wippich himself. So I'm Mark Tolbert. I am President and CEO of Toptica USA, and we focus on all things in North America. To give you a little bit of a sense of who we are, this is our current state-of-the-art facility that we just opened in Rochester, New York, that's committed to research, development, product development, and essentially doing all of the things that we need to make our market successful. As you can see here, Toptica is globally where quantum is needed. And we're excited to continue to drive that. We've been doing that for 25 years. We celebrate 25 years this year. Today, we are just over 450 people. We're about $100 million in size, so we're a good medium-sized company. Of that, we've got more than 100 R&D scientists, and more than 60 of those have been committed to quantum. So we're excited to have such a critical workforce to enable the quantum commercialization. The largest challenge that continues to come forward year after year, and we've heard this for many years, is the sheer number of wavelengths. We've heard that already today, and that continues to be a problem. So our solution to that has been offering all wavelengths. Simply put, we've been doing it from laser technology, and we've turned it into a slogan for the company that we will continue to drive. I was reminded earlier of the chaos of quantum and the chaos of the laboratory. And although I have to admit, I love seeing all of these blue boxes in the lab, and it's also fun to see world leaders be interested in that as well. It's about commercialization of quantum technology today, and that's what we're here to do. Toptica has been evolving the lab from that chaos into something that is useful. With the introduction of our T-Rack solutions that include lasers, frequency combs, optical systems, and everything that belongs on the optical table, we've turned it into a product today that's ready to commercialize quantum technology. This is an integrated and portable system that allows robustness. We even were able to experience during COVID that our systems can operate remotely for literally tens of thousands of hours. So commercialization of quantum is already in the early stages. We also believe in collaboration. It's the key to the success of this community. Whether it's a major flagship program where we can actually drive the innovation and act as a system integrator, or just relationship building of building community, whether it's QED-C or QUIC or other entities throughout the planet, we're here to drive collaboration as well. So whether you have a product need that gets involved today to build your computer, your quantum communicator, or a quantum sensing application, we can help you with that today. We also have products that go compact with our ECLs and our butterfly packages. And we continue to do development towards photonic integrated circuits, and we'll continue to drive that as the markets emerge. So again, all wavelengths. We will be here to solve your laser problem. We want the laser to be a commodity. We want you to be able to focus on the physics package and the applications in the end. We want to be your laser supplier for that. What's our ask? The biggest ask is to keep collaboration open. There's no one national interest today that dominates the need for lack of collaboration, and we need to continue to drive innovation as well. The relationship between science, government, and industry is more critical now than ever. The second ask is if you love quantum, join us. Come join us. We're hiring like crazy. We hope that you'll join us, and we'd love to have you as part of the team. Thank you.
Hello, I'm Scott Davis. I'm CEO and one of the co-founders of Vescent. I'm also on the QED-C steering committee. And today I'm going to talk to you about solutions for deployed quantum, getting quantum out of the lab. It's something I'm very passionate about. I'm having clicker problems. Got it. Okay, so who is Vescent? We have a rare quantum 2.0 team. In our DNA is quantum. We come out of JILA and NIST. One of my co-founders built the experiment that did the first BEC. One of my partners, the VP of technology, he built some of the very first frequency combs. He worked with NIST and Jan Hall's last grad student. And one of my other partners, so we understand exactly how hard the requirements of quantum are. One of my other business partners has decades of manufacturing experience. So we've got the combination of both the rare quantum know-how and the core manufacturing. So solutions are deployable. Quantum can leave the lab, and it already is. This is somewhat notional, but we have hardware in space, we have hardware at sea, we've done demos in the air, we've got deployed systems on land. It's hard, but it's possible, and the possibilities are very tantalizing. Where do we fit in? We are a tier 1 supplier. So we manufacture subsystems that go into the people that make the systems. And we sell across the quantum ecosystem. We've got customers that are doing communications, computing, sensing, timing. We're really enabling the Quantum 2.0 ecosystem. We have a line of products that support scientifics. What I'm talking about today is our products that support deployed. So this is a graphic that sort of says what we're about. And so up on the left is the first self-reference frequency comb, Ted Hensch's lab, an amazing experiment. We now have frequency combs that are turnkey, they just work for the laboratory, and I'm very excited that we've got frequency combs that are OEM modules, very compact, very low swap, reduced swap and cost for getting it out into the field. And so what do I mean by that? Well, let's see if this plays. So we are beating the crap out of these combs. We beat the crap out of everything. We're shaking them, we're baking them, we're trying to break them. There's one of our oscillators on a vibration table. So we're putting these for customers into demanding requirements. We're maintaining the performance under vibration. This is not easy. Quantum is hard, but it's happening. We're doing it. We also, this is showing environmental chambers. We've got our oscillators that are operationally verified from -10 to 75 degrees C. We've got customers that require that. And so they stay mode locked, they keep working under those ranges. And it's deployed. It's not hypothetical, it's happening now. And so we've been part of an at-sea optical clock demonstration through RIMPAC. We made the combs for that. We also are part of quantum sensing, doing methane leak detection. We've got dozens and dozens of units that are enabling our customers to be out there in the field running 24/7. They're running right now. It is not some hypothetical in the future, it's happening now. We have a line of CW products where we take the whole electronics and the whole referenced against an atomic species for enabling clocks, gravimeters, inertial sensors, anything we need to trap and cool atoms. And we got cold atom systems, our customers that are deployed all over the world. And so we make the laser systems for that. We're not standing still. We are also in the process of commercializing ultra-narrow 9-width lasers that do not require a big ULE cavity. And so here's an example of performance, about a 15 hertz line width, incredibly clean spectrum. It fits in the palm of your hand. We just shipped the first couple beta units. We continue generational improvements on our frequency combs. I blurred it out there for a little bit of IP, but these are now the size of credit cards. These are being designed into our next products. They're going to be commercially available soon. And we're already shipping some units out to customers. We also do development with DFMA from the beginning. This is incredibly important. So if it's going to leave the lab, it cannot be built by PhDs. And so we work with the manufacturing group, works with the R&Ds right from day one. So they don't design something that can't be produced by techs. Our products are technician produced. They're not produced by PhDs. All right, we've got two buildings two facilities in Golden, Colorado. I took pictures that showed the nice mountains. This is me. I'm happy to talk to anyone, and thank you very much.
Hi, I'm Gordon Morrison, Vice President of Engineering at Freedom Photonics. Freedom Photonics is a company that started out about 2005, a small company with 3 founders. It was self-bootstrapped and was in the photonics industry making Pixon lasers for niche applications initially because it was self-bootstrapped and growing out of really nothing. It's always been self-funded. Up until recently when it was sold to Luminar, a large LiDAR company. Freedom Photonics is an overview. We are vertically integrated in the sense that we make PICs. So at the top of the screen there, you can see an example of a rubidium wavelength photonic integrated circuit that was monolithically fabricated. It's got multiple lasers on it, photodetectors, shutters, modulators, all built onto the same functional chip so that you can do beat notes and so forth. We can also package these components. We do packaging with technicians in our own clean room, Class 10K clean room. And then we can take that and put it in a module. So that butterfly package ends up in a module like that blue box you see there, where we can control the laser, the PIC in fact, and match the application at hand. We also have been involved in quantum sensing applications in terms of the physics package itself. Early on, we found that because we can package lasers and package PICs and work with micro-optics, that expands very nicely into building up the optics around the laser and the PIC so that you've actually integrated them with the sensor head as well. Products that we have that are useful for quantum applications at this time would include our 780 and 795 distributed feedback lasers. We've put a lot of time and effort into making sure that these are mode hop free, and we've been burning them in for many thousands of hours now, showing that they are wavelength stable. We use them also for development of some of the sensor heads and so forth that we work on with partners. Another area that's interestingly important is the O-band DFB. So we do work in other areas like telecom and so forth. The O-band DFB was really thought of as something that would be useful for data center type applications, but it turns out it's useful for Rydberg sensors too, 3-photon type E-field detectors. We can get hundreds of milliwatts out of these DFBs. They're single mode, and when we can tune them across about 4 or 5 nanometers, because they still put out 100 milliwatts, even up at temperatures like 85C, which is very impressive for indium phosphide. Speaking of high power, we also make power amplifiers, and we're seeing 4 or 5 watts CW on indium phosphide and greater than 10 watts on gallium arsenide. This can be integrated with all kinds of different platforms that we have for photonic integrated circuits at Freedom Photonics already, and this is finding a lot of play in the quantum space as well as many others for us at Freedom Photonics. Lastly, I will mention that we do have a product line of fast tunable lasers. Again, that has come up as interest when we talk to people who are looking at Rydberg sensors where they want to be able to hop across channels pretty quickly. And our O-band tunable laser line does go from down in the 1250 nanometer range all the way up into the 1700s. So we make fast tunable lasers across that broad portfolio of wavelengths. We also have ongoing development work, of course. I would say that quantum is a fairly nascent technology field for us to be operating in compared to things like remote sensing and telecom and even perhaps LiDAR to some extent. Freedom Photonics is developing hybrid integrated, photonic integrated circuits as well. The platform we tend to lean on, although we take other approaches as well, is photonic wire bonding. This is a technology, you can see right there at the top, a scanning electron micrograph of one of our Freedom Photonics tunable lasers directly photonic wire bonded to a fiber. So you take care of all that mode matching nonsense and chip placement nonsense just by having the tool and writing a waveguide from the chip to whatever other waveguide you need to. So that works for narrow line width lasers, for integration with lithium niobate. It gets the 3.5 light onto whatever other platform you need. We're also working on the development of physics packages. So we partner with other quantum sensing groups. We're not a bunch of quantum physicists. We are photonics integrated circuits designers and engineers and physicists. But we are partnering with people who have expertise in the quantum world so that we can take our photonic integrated circuits and apply them to solve the problems of size, weight, power, and cost. As a final example, down at the bottom there, you can see some more of the micro-optics alignment we've done to prototype solutions. And on the bottom right, you can see some of the more highly integrated module type work we've done as well, where we've taken a very complex photonic integrated circuit, integrated it with micro-optics for locking, and then we've got all the control electronics built in there as well. And now, of course, under the Luminar umbrella, we are partnered with Black Forest Engineering that makes ASICs, so we can take those highly complex multi-layer PCBs, shrink them down even smaller, and make them into an ASIC-controlled module. I think that's about it for the slides here. But we also are hiring, and if you've got an interest in working at Freedom Photonics, please come talk to us. We're also interested in partnering with people who are better at quantum physics than us and who would like to use our photonic integrated circuits and lasers. Thanks very much.
Hello, everyone. Thank you for joining here today. So I figure I would start with a quick tidbit about the name. It comes up often. So are we Infleqtion or Cold Quanta? The answer is yes. But Infleqtion is a products company, and Cold Quanta is a brand. within that products company. It's largely for our research services, and it's also for a lot of what I'm going to talk about today in the vacuum packaging and physics packages as well. In addition, it's a house of brands. So we have an addition this year called SuperTech. This is a software company in Chicago that we acquired, doing quantum software. They do a variety of applications in that field, and they are just an excellent addition to the team. So many people know Cold Quanta, at least recently, at least for this market and this applications for the quantum compute. And let's see, yeah, up here. And so we do have a quantum computer that utilizes neutral atoms. And I'm not going to get into too much detail about that today. Today is a little bit more about the pieces and parts, as you've heard so far. But Infleqtion actually does many things. We have commercial and developmental activities in clocks. We have developmental and commercialization activities in quantum RF receivers. We have commercialization and developmental opportunities in inertial sensors as well. And how do all of these things tie together? They tie together with that thing in the middle, the physics package. And so when we say physics package, what does that mean? It means the vacuum system that contains, in this case, the atoms or the ions that are used for the core of all of these applications. And this is really the heart of Cold Quanta, the origins of it, even though we're doing a wide variety of applications from that now. So I talked a little bit about this. We do neutral atoms, ions. We have microassembly that goes along with these things. And we are producing even more integrated versions of these as well, along with vapor cells. So one of the key things that this piece of our business has is it's actually firewalled from the rest of the business. So because a lot of the times when we sell these physics packages to the quantum market, the customers for that can in fact be competitors of the systems that we're producing at Infleqtion. And so when we engage with those customers, there's a complete firewall there, and our internal compute teams or our internal clocks teams don't even know who we are talking to when we talk about producing the physics packages. So, what does this look like going forward for quantum in the future? This gives you an idea of the scale of the systems right now. This is Albert. This is a quantum matter machine. So we build this completely in-house. We can sell this as a completed device or as a cloud service. It is a machine, quantum matter machine, that produces Bose-Einstein condensates, and the users can manipulate them in a variety of ways. Inside that machine is a physics package, and it looks about like this. This one is what we call our double knot system, and it's about this big or so, and you can see it kind of lives right in here. But we're on the path to making these even smaller, and I'm fortunate that none of my other colleagues here brought show and tell. Well, I did. So this is one of those physics packages. So this is for neutral atoms. It has a two-dimensional magneto-optic trap here, a three-dimensional magneto-optic trap here. It has an ion pump built into it. This is completely permanently sealed and under vacuum right now. So that's the neutral atoms are. Let's check the other pocket. This is an ion trap, completely permanently sealed. A surface ion trap goes in here. Again, this is the ion pump. This is for a room temperature operation device, and this will achieve low 10 to the minus 11s going into 10 to the minus 12 torr. We also build a version of this that could be operated at cryogenic temperatures. Again, completely permanently sealed. So this is the direction that the physics packages are going, and I think you saw a flavor of the rest of the panel here, where the rest of the infrastructure has to go, because it doesn't make any sense to have this and then have an entire table full of beautiful Thorlabs equipment. That isn't fieldable. So I think that's the path we're on. The panel here has indicated they're all headed in this direction, and collectively, hopefully, we can get there soon. So finally, my goal here today is to not to give you the full overview of Infleqtion. We do so much stuff, that would be an hour in itself. This is about the physics packages today. So I hope to talk to anybody in the audience who wants one of those. But I don't want to neglect the other parts of the company. If you are interested in quantum RF, if you're interested in atomic clocks, if you're interested in quantum computing, please come see me. If you're interested in quantum software, I would love to talk about that, and I will turn you over to the right people who know way more about the quantum software than I do. Thank you very much.
Hi, everyone. It's such a privilege to be here and to talk to you about Riverlane. We are a quantum computing software startup based in Cambridge, UK, but now also have a US presence in Boston with about 90 employees now. And what I want to talk to you about today is how control systems and work on control systems will make quantum computing useful sooner. So, why quantum computing? Why are we so excited about quantum computing? Well, I am a chemist by training. In a previous life, I was a chemist. And I am excited about quantum computing solving really thorny chemistry problems that will help us build a more sustainable economy. For example, if we want to go to a hydrogen-powered economy, we need to improve a process called steam methane reforming that produces the hydrogen. This is a catalytic process that uses a lot of energy, and we need to improve these catalytic reactions to reduce the amount of energy that goes into it. And we could revolutionize this, the R&D that goes into this, by being able to compute the properties of the catalyst rather than doing trial and error in the lab. On a classical computer, this is currently impossible. On a quantum computer, we would need 10 billion operations. We would need a machine that is able to do 10 billion operations on 5 million qubits. Now, I think you all know that today we have quantum computers that are amazing, that are heroic feats of engineering and physics. But unfortunately, they're around 500 operations on 20 qubits large. So we've got a really long way to go. Luckily, there's so many people here that are up for this challenge in terms of scalability and also in terms of the error correction that is needed to actually get to that sort of computer. So let me tell you a bit how today's sort of experimental setups look and how the different parts that we've been talking about come together to make a qubit or a couple of qubits. So this is an experimental setup that we have today. It's a bit complicated, so let me disentangle it for you. We obviously have lasers. This is an ion trap setup that send pulses to our atoms in a trap or to our ions. And these get modulated by acousto-optical modulators. And it is a very complicated control system that sends RF pulses or that produce the RF pulses to really modulate these laser pulses in just the right way so we get a qubit out of our atom or ion. So we at Riverlane are working on the control system, on making it more scalable, on making it ready for this big challenge of quantum error correction that we all need to face. So our control system is called Delta Flow Control. It is a scalable and error correction ready system. So it is designed with all the requirements from quantum error correction in mind and has a scalable, decentralized architecture. It has just the right kind of timing and pulse control and precision that people in the lab need to be able to concentrate on the physics. And it is intuitive and user-friendly with an amazing front-end and software stack on top. It is also deterministic, so you program and you get what you program. And we are very proud to be working with the leading labs in the world, including academic labs like Tracy Northrop Lab in Innsbruck, but also commercial customers. We're currently focused mostly on atomic qubits, so cold atoms and ions, but we also work with superconducting and silicon qubits. So, what now? We are convinced that a better control system isn't only important for quantum computing, but that it will galvanize other discoveries related to AMO physics, for example, in atomic clocks, for example, in quantum sensors. So we are looking for partnerships with like-minded companies and institutions that want to make this process of building large-scale quantum computers and deployed quantum 2.0 tech like clocks, sensors, etc., to professionalize this, to make everything smooth for the user and make error correction and scalable systems. And this is why I'm here today. Thank you very much for listening, and do get in touch.
Great, thank you. Wow, loud. All right. So let's have a panel discussion. All right. What are your quantum commercialization customers getting out of your solutions today? Why don't we go backwards? Why don't we start with you?
Well, they get a real partnership on some of the most thorny questions in terms of the engineering that needs to go into large-scale quantum computers, right? We're just at the start of that journey, and the control system is such a big part of it. Currently, most of it is FPGA-based. At some point, it may be ASIC-based. And so this is what we provide.
And Riverlane works with all 8 modalities of quantum computing?
We work on the control system side. We currently work mostly with ion traps and cold atoms. We do have partnerships in the other modalities as well, in the other qubit types, especially in our work on error correction, which I haven't mentioned that much today.
Okay, great. Chris.
Yes, this one, okay. So there's a couple things that our customers get out of this. You know, we build hardware at Cold Quantum. We allow these customers to take that physics package that I showed you. We will wrap a full system around it, and we will sell it, and basically we're enabling quantum to be deployed. We need help from the other companies like the other ones here on the panel to make that happen. So really, that's what they're getting out, actually deploying quantum systems. For things like compute, we offer kind of an intermediate solution where we have a quantum computer on the cloud, or we have a quantum emulator with the quantum matter machine on the cloud. So it's kind of an intermediate offering, if you will, that allows people to access a Bose condensate from their home and start designing their own atom interferometer, not by simulation, but by actually manipulating a Bose condensate.
Great, great. Gordon.
Yeah, is this on?
Yeah.
Most of our customers are actually getting a couple things out of Freedom Photonics solutions. One, of course, is just some of our standard packaged DFBs and tunable amplifiers, that kind of thing, where frankly it's still being used to develop prototypes and take it from the prototype stage where it's on a large bench top and is being shrunk down to the point where it's still a prototype but can now be field tested, moved around, taken outdoors, and prepared on that journey to the marketplace. We also are able to take a lot of our know-how from a wider range of photonic integrated circuit applications. So we do play in the telecom space. Obviously, we have our largest customer now is our parent company, Luminar. And we also play in remote sensing, gas sensing, that kind of thing. We can take all the know-how on photonic integrated circuits and how we solve problems there and really help educate people who have a huge amount of experience in the quantum space, but maybe don't know what kinds of picks do what and would best solve their problems. Yeah. And that's what we've brought to the table, and I think we're doing a very good job of growing a lot of those prototypes into more and more maturity with our partners.
Great. And Scott?
We sort of have 2 classes of customers. We have scientific customers. For those folks, we kind of try to find a performance niche. We got some pretty serious competition in scientific customers, and they make some pretty spectacular products, and I decided it wasn't good business to go head-to-head with them. For our emergent, nascent customers that are looking at getting things out of the field, we make them rugged. We make the systems rugged, simple, full system solution with all electronics. just so it solves their problem. And a lot of times we're the only game in town.
So why is that?
Because the markets are teeny, and so it takes a small company like us who will take a chance saying that this is going to grow. So, you know, Coherent's not going to touch a customer that says they're going to buy 10, but we will.
Yeah, Mark.
All wavelengths. I mean, it's the robustness, it's the reliability. We give them what they need now. We give them the ability to evolve their product while not having to worry about the laser technology. We give them performance, we give them community, we understand their application. But we're focused on the laser and the things that go around the laser. If they need help building the optical system up to their physics package, we can do that too. And when they can provide us with a market and they're ready to move the market forward, we can help them with that scalability as well. So again, our focus is to really enable the communication, the commercialization of the quantum community.
So, how much of Toptica's business is in quantum? I don't think you said that. You said how big your company is, but how much is in quantum?
More than half of our business is actually in quantum today.
So you're the market leader when it comes to lasers.
Well, we have a quantum market.
Yeah, okay. All right.
You're making money.
All right. Sasha.
Well, clearly the benefits of fiber laser technologies.
You're on. Yeah.
Clearly the benefits of fiber laser technologies, the scalability, the industrial background of it, which allows 10,000 of operation hours, turnkey. I know it's boring for scientists, but hey, it is reliable, right? It's turnkey. And of course, a clear journey to scale the power levels from hundreds to thousands to millions of qubits by just scaling the amplification part of it. That's, I think, the main benefit of fiber lasers. We've seen this in other industries before where fiber lasers have changed and transformed the technologies. At that point in time, it was literally disruptive.
You want to add something, Marco?
I love surprise questions. I can give you a few examples. One I showed before is actually the VCSEL used in the CSAC. Another one I can add is, and you saw, if any of you was at the plenary at CLEO just before COVID, Chris Morrow was showing some of his activity at IonQ using our UV mod-locked laser, the Paladin, as a key element for operating on this ytterbium ion system. Another one I can mention is our green lasers used in system using nitrogen vacancies. And then last but not least, moving from laser to something else, Coherent has capability to manufacture polycrystalline diamond, and just recently we acquired license and capability to do also single crystal diamond, which is an important material for quantum application. So this is just a few examples of something that we already have done.
Great, thank you. So I'm going to go right back to you, Marco. So what does your company need from the ecosystem to accelerate quantum solutions at scale? You work for a company that does over $4 billion a year in lasers and optics around the world. You have multiple fabs. You could get in tomorrow and solve these problems. Feel free not to answer the question.
No, I mean, I think it was interesting. Scott gave an answer for me. We need more than 10. If those are big lasers, if they are chips, I think it's more than 10, right? I would say we have these a lot of capacity and capabilities. I mentioned before the various platforms, so this includes indium phosphide, gallium arsenide, gallium antimonide. Also, it might be contradictory, but I mentioned before how flexible is some of our platform, the OPSL platform, that can be tailored to many different wavelengths. Not fully tunable like TISAF, but tailored by design on specific wavelengths. So it looks like we can do every wavelength, but in reality, I still think that there is a need for consolidations, because it doesn't...
On the atoms, on the species?
I think so, because producing 100 different wavelengths, it's not
Somebody
the
did
best
that already.
Yeah. Yeah, they're very good, right, yes. But I think for scaling up, for expanding the market, I don't think that having a huge variety of wavelengths is very conducive. There is a need for some consolidation, in my opinion.
Great, great. So that's a great key up to Sasha. So NKT now is targeting 4 species. What, strontium, barium, ytterbium, and
Strontium.
strontium. So neutrals and ions.
We actually appreciate that the ecosystem has taken already decisions, right? To
Some.
focus on dedicated species, which allows us to scale and literally to produce with volume at the right price points.
So
solutions.
why those 4?
Because that was the highest demand in the field, both for quantum sensing as well as for quantum computing.
Okay, thank you.
So for us, it's focus.
Yep.
Our decision is not to go for all, but going for the right ones and make those great successes.
Thank you. Mark? Oh, wait, we need Mike. Hello? Bill? We need a mic? No, now you're off. All
Hello?
off.
No, I'm working. Am I working? Yeah, there.
Hello? That one's worse.
This is a challenge, 7, 8 of us. All right. Are you working now? Not yet. Not yet?
Go for it, Scott.
I can chat while
Okay.
you get your mic. It's exactly what other folks have said. It's market. There's market uncertainty. You know, we're taking some gambles that some of these nascent applications are going to take off. They may not, and so it's understandably a gamble. I believe that some of them will, and we keep looking at sort of which way the sands are going and trying to place our bets and pick our pull shots, whatever businessy metaphor you want. But it's, right now there's not a winner. There's so many atoms. I think your down select is a good one, and I think it's starting to happen, but it's still taking some time.
Yeah, is Mark's mic working now? Yeah. No, still not. Get Scott.
Scott and I are close. I mean, point blank, it's too nascent. It's too early to make the determination. We see the same thing in the scalability of wavelength and the drive to that, and we agree with everything that's said up here so far. And that's why the biggest thing we need to continue to do is keep the lines of communication open, keep the collaboration open, and focus on solving a real problem. I mean, that's what's really needed.
Gordon.
No worries.
Sure. In terms of, can you hear me okay?
We need Mike.
Or do I have to listen? Hello?
Oh yeah, okay, you're good.
Get a little closer to my mouth. Is that working?
Yeah, you talk louder.
Yeah, in terms of what our company needs, I think volume is maybe something that comes to mind. So there is risk in the quantum regime, and we can leverage technology from say a larger volume area and try and pull it into quantum where there's a good fit. So working with the ecosystem, as it were, to identify those opportunities is certainly something we want to do. But what we can't get into is a trap that I sometimes see where a potential customer has this great idea. I want a photonic integrated circuit that does that. Can you guys make this? Absolutely, yes, we can. And then they say, well, I've heard you can get photonic integrated circuits like that for telecom, and they're about $10 each. That is true. But the fact of the matter is they want to buy 10 or maybe 100 over the course of a year. And that might go on for many years, but the effort, and I know this because I've worked in the industry, of making something at $10, a photonic integrated circuit, is enormous and incredibly expensive, and it's associated with volumes that are in the millions per year. So we have to kind of identify realistic markets where, and there are some, where a photonic integrated circuit either is going to be made in high volume for quantum, or alternatively, where there is a very high-end market that can support a fairly expensive photonic integrated circuit, as far as photonic integrated circuits go. And to that end, actually, I think it is worth pointing out that while I've seen sort of estimations that, within 5 years, the annual market's like $1 billion, and maybe PIX is a piece of that. When you look at the amount of money that governments are actually investing in quantum, it's a much larger number. Why is that? Well, it's because it's enabling a huge number of new technologies and infrastructure throughout the world. And one question I have is, how do we take some of that value added, the value added to the world that I believe quantum will bring, and funnel some of that into the development that is necessary to get us there?
Great, thank you. Chris?
Yeah, I think that one of the key things we need is for, as a company at Infleqtion, is we need quantum computing to succeed. And in order for it to succeed, it has to scale beyond 10, 20, 50, even 100 qubits. It has to go to 1 million qubits.
Error corrected.
And error corrected. And so in order to make that happen, there is no way that can be an optical table lab-based solution. Everything we just talked about has to happen. So it's not this situation where quantum computing succeeds and then we are able to shrink it, right? Actually, we have to do all that in parallel just to make it succeed, because there's no chance to get to 1 million qubits on an optical table. And so, but we also need early adopters. Again, for Infleqtion as a company, the clocks, the RF, the inertial, we need early adopters to get their wallets out, get the applications going, buy low volumes of these, and get that ball rolling. Early adopters are critical for every industry. We're no different.
Great, great. Yoni?
I've got two answers to this, and the first one is perhaps a bit left field in this audience, but it is a more robust answer to why. Why do we need these quantum computers? We sort of assume that once we have the machines, they will be useful for something, but we really need to motivate it better. And I want to point out that actually the biggest advances in terms of making the size of a useful quantum computer smaller have come from algorithms, applications, quantum information science, research in the last couple of years. And we need a lot more of that from the algorithm side to shrink the size of a useful quantum computer, because we can sort of save resources by using the qubits better. That's my first answer.
So making it more efficient.
Basically, like better algorithms, so we can make more of the qubits we have. And the second answer is about figures of merit and standards. So the control systems market is just about evolving or emerging. Just a couple of years ago, everyone was deciding, oh yeah, we're going to build our control system ourselves, every quantum computing company. And this is changing now, because everyone is sort of like getting aware that this is an enormous problem where we all need to sort of work together. But we can only do that productively without like IP models and without overlaps and interests, if we have better interfaces and can build to standardized figures of merit that we all agree on. Like our control system has to do this exactly with that sort of performance to get that sort of qubit quality out. And to a large extent, these are also research questions that still need to be answered. But this is also where I feel like a round like this can contribute a lot.
That's the point.
Exactly.
So I'm going to expand on that just for a second. So laser companies are daunted with all these different wavelengths, right? So Toptica's addressed the research market. NKT is taken a bet on a smaller subset for a build-out market. Others are doing probably the same. When you are dealing with ions and neutrals and helping quantum computing companies, is that the same solution?
It's not. It is definitely tailored to the specific species and even to the specific lab. However, there's a core that is quite similar across labs that we can sort of reuse, if that makes sense.
Okay, great, great. Thank you. Okay. What market segments in quantum are commercializing customers pulling the hardest for? You're probably going to all have different answers. Maybe some of you are going to have the same. But I want to go back to Marco. What I understand is Coherent sells lasers into the research market of quantum. You're not really in quantum, but you have lasers that work for other markets and they work for quantum, right? But of the four, where do you get the most customer pull?
And that's a tricky question. So first of all, you are absolutely right. A certain part of our participation in this market was because our platform, not specifically designed for quantum, were actually a perfect fit for some quantum application. And of course, we love that, right?
Sure.
So from what I see here, although Coherent as a big player in networking, at this point, I would not put quantum network on top of my list. I would say that quantum computing, as it was pointed out before, also is the area which is funded with the deepest pocket. It seems to be also the area where the cost of the system, of the laser system, the laser package, it seems to be more cost tolerant from a point of view of the laser package. And probably there is also a higher component of lasers, both in power and in quality, than in other systems, with the exception of clocks. On the other hand, clocks, in my opinion, require more miniaturizations. So I would say, from my point of view, if I were to pick one, I would pick computing.
Okay, great. Sasha?
Well, I think that's a very interesting one. Quantum sensing in my play takes place as we speak. As we're sitting here, the market takes place. So with over 15,000 fiber lasers in the world of sensing technologies, we are right now strongly engaged in the sensing market because we have all the core technologies, the form factors, the reliability, the performance is all in place. However, as we have heard here as well, quantum computing is evolving, it's maturing. So we see there actually quite interesting avenues into this market. In networking and in timing, I do believe that there are similarities in sensing with timing. Atomic clocks, miniaturization, requirements are along the lines there. On the research side, material research, material developments, we can see in quantum key distribution a lot of exciting things, and that's where our ultimate opposite technologies, our supercontinuum lasers, are making great use of this, because you have the variety of light in order to characterize, to quantum characterizations, to do quantum efficiency measurements. So if you ask me commercially, I think sensing and computing is highly interesting. It's timing in between, while networking and timing in itself will take great movements as well.
Thank you. Mark?
We're working. We're kind of back. We've got some volume, I know.
Let's go.
I enjoyed it too. The short answer is all of them, Mark. I mean, quantum computing pulls the greatest draw. And if you're looking at actual revenue where they're looking for uptime and reliability, then it's quantum computing. The rest of them fall into a need that actually drives the capability. We're still not getting time.
So, no problem.
So as I was stating, quantum computing is actually driving much of the commercialization for reliability and uptime. When you start looking at sensing, timing, and networking, of course, those all participate. But you could look at if you're considering it from a commercialization standpoint of monetary purposes, then you could look at the flagship programs. In those particular cases, they're looking for ultimate performance. So from a market, it drives the technology that can then scale into something that's useful afterwards. But uptime and reliability, they come to us for computing.
Okay. Scott?
I'm going to give a different answer. Most of our pull is from timing, and sensing comes second. In both timing and sensing, quantum supremacy is today. Atomic clocks have been quantum supremacy for over 60 years. I mean, 60 years ago, when the first atomic clock, it was 1,000,000 times better than its classical analog. And the atomic clocks that are coming out now are going to be 1,000,000 times better than what is widely available. The world is dependent upon GPS. That's a tremendous vulnerability. There has to be a backup to that. That's real. It is coming. I feel very confident about that. And so we have customers saying, oh my God, can you make a comb that can fit on this platform? Can you make cooling lasers that can fit on that platform and survive these environments? Do you believe their volume projections? Not all of them, but the application and the physics, that's real. So,
Gordon, thank you.
Timing and sensing are, I would say, equally split for the customers that we've been working with. We don't actually have a customer that we're working with at the moment in computing, but we have been approached occasionally with queries there for much larger volumes than say sensing or timing would have. So it's definitely an interesting field that we'd like to try and find more synergy with. But right now, I'd say sensing and timing are the two areas that we're actively working in and have customers that have products under development.
Chris?
Yeah, I think I would echo Scott and Gordon both. And maybe even take it one level higher and just say national security. That encompasses inertial clocks and quantum RF as well, which we have a big pull for right now. So, you know, from a commercialization point of view, and especially if you interpret that as a little more near term, then those would be the ones. And then going back to compute, make it work.
Well, we work in quantum computing mostly and are just now exploring whether our solutions might also be useful for other quantum applications such as clocks. I can give a nuanced answer on when I think quantum computing will really have market pull. So our current best guess is 10 years based on sophisticated resource estimations that we do, especially on chemistry and also fluid dynamics applications. And as I said, the dark horse there is algorithms development, both in the applications field, so better chemistry algorithms, but also in the quantum error correction schemes and codes field. So that might really bring that timing forward.
So quantum networking probably needs error correction as well, right?
So I would say it the other way around. Big quantum computers will need quantum networks because they will be modular.
Sure. Right.
But yeah, and they will need error correction.
Right, thank you. Okay, so I'm going to start right back at you. So what is the most common misconception about solutions for deployed quantum?
Oh, and I'm myth busting.
Yes, you are.
I'm myth busting. I mean, there's a lot of misconceptions that fly around that, quantum computers will be useful for everything, and they won't, right? They will be useful for very specific applications in very specific circumstances, and we really need to find that wedge where they will first be useful in an industrial setting. And we have not really found that wedge yet, I think, as a community, if we're very, very honest. However, the promise is obviously enormous. Yeah.
Great.
That would be my answer.
Great. Chris?
This is a tough one. I would say that, one of the misconceptions is it's too hard, right? People think quantum's too hard, it's too sensitive. You'll never be able to get that into the field. Well, that argument has been used.
That's a lot of experts say that in this conference,
Yeah, but that line has been used how many times in optics and photonics? It's too hard, and yet 5-10 years later, there it is in a package in the field, right? It's money, it's effort, it's markets that will push it past that. So we're in a phase right now where, yes, some of these things really are very, very difficult. It doesn't mean they can't be done.
Yeah.
I'm certainly up for the challenge.
Mm-hmm. Gordon?
Well, first of all, I do agree with Chris very heavily on that. Too often I've heard people telling me that well, that'll never work, and then it does. Whether it's at the laboratory level or, as we can easily point to, in commercially available products right now. I guess the other misconception that I've already alluded to is you'll find there's scientists, people, government, companies that have a great idea for a quantum product, but again, the volume has a mismatch with the prices they think of for the components. So we're at this stage where we're trying to bring out quantum technology, new quantum products, and if you borrow from another industry where there is a very high volume and assume that the price on similar components are going to be the same for a much smaller, albeit much higher end quantum deployment, you're going to fail because the market doesn't support that volume at that price. So that's definitely a misconception that we stumble across occasionally.
Great. Scott?
I will echo what Gordon said. I think there's a lot of market misconceptions. In order for this to go anywhere, it's got to be market viable, and everybody in the supply chain and the value chain has to be making money. And if your laser is going to be 2 orders of magnitude harder than a telecom laser, and your volumes are 3 orders of magnitude less, it's going to cost more. I'm sorry, it just is. And so people need to understand that. I'll be a little bit contrary to some of the folks. Lasers and photonics are freaking hard. They're not electronics. And we get customers saying, I need a part in 10 to the minus 14 fractional stability, and it's got to survive on a tank. It's like,
that's really freaking hard. It's like they think that you can just do it, but so you got to get them to pony up the money to get the development done, and then you got to make that make sense with what the market reality is short term, and so you got to navigate that whole space. So market realities and quantum's pretty freaking hard. There's still a lot of technical and market risks associated with it.
Yeah, and I agree. Can I borrow your mic again?
Mike?
Oh yeah. Sorry. That's all right, I got you.
I agree. I mean, the scalability to the electronics is one of the most difficult challenges. But I think the other misconception is that the market won't bear it. The short answer is yes, we can scale them all. Yes, they don't need to be $10 a piece. They can scale at a rational level that the market will bear it. I mean, we're the perfect example. First laser ever built by Toptica was for Bose-Einstein condensation 25 years ago. It bared it. The market bared it. So it is scalable. So let's not focus on necessarily, let the laser experts focus on the laser experts, on the expertise of the lasers, focus on the physics package and the problems that they can solve. And if we find problems that are solvable, then it'll be scalable.
Yep. Sasha?
I think it's about timing in terms of management of expectations. Yeah. I think we have all the building blocks we need already. It's about the engineering part, getting it together and finding the applications, which then actually can provide the proof of concepts that quantum actually provides a commercial value. Some people talk about quantum supremacy. I think it's the commercial value proposition. As soon as that gets shown, it will happen. And in between is the expectation management of the time as it takes to make this all happen. Because I've seen so many bright people over the last years putting a lot of efforts in making this happen. I'm convinced it will happen.
Yeah, great. Marco?
Well, my answer, of course, is focused and restricted on the laser field. And I would say that not everything has to be complicated, complex. And I can give you a couple of examples. On one hand, you have devices like the VCSEL I mentioned for the CSAC. The specification of that device are extremely tight. But on the other hand, you have very simple diode at 800 nanometers that can be used to make a quantum key distribution using parametric conversion to get 2 photons close to 1550. Those are inexpensive diodes. On the other hand, we sold some lasers, green lasers, for quantum computing in nitrogen vacancies. And those are 15 milliwatt lasers of the same type that are used for life sciences to excite fluorescence. So not everything is complex. So this is one of the misconceptions I see.
Great. Okay, I'm going to skip to this one. So with all of you presenting today, sort of the idea here is partnership, right? So with the companies that all presented, where do you see that you could potentially partner? Riverlane.
Okay, yeah, well, we see tons of potential. We're obviously all in the same boat in terms of solving these scalability challenges, and I'm talking about scalability of technology, of quantum computing technology, right? So we need to improve lasers, we need to make lasers much more user-friendly, much more plug and play. We need to improve control systems, make them more scalable, make them more plug and play, and so these sort of complement each other a lot, right?
But Riverlane also wants hooks into lasers, right?
Yes, in a way, yeah, sure, exactly.
Physics packages.
Physics, exactly. For physics packages, exactly. It might make a lot of sense to sort of build control systems and so these physics packages together, for sure, exactly. Something that we also think a lot about is sort of like the commercial scalability. So control systems today are still very, very expensive. So, you know, we're talking, you know, 15K or so for, at least for just a couple of radio frequency channels, and they will need to come down in terms of price when we want to have like millions, billions of RF channels. So we're looking to some of the experiences also in the photonics and laser industry in terms of, you know, getting price down, getting things to production level. I think we can learn a lot from them.
Yeah, great. Chris?
Your question presupposes that we're not already partnered. I can say that the majority of people here.
What you're doing today and what else you want to do, right?
Yeah.
So
yeah.
I have to keep it open-ended.
Right. Well, I don't want to state the obvious. We don't make lasers. Infleqtion doesn't make lasers. We have to modify and adjust and tweak them and do other things with them, but we generally buy our lasers. We work with others to get photonics pieces and parts. So there's a lot of partnering that happens, and I think, you know, I didn't mean to tease people with the size of the physics package, but that everybody has to go there, and so the partnering and that scaling down, I think anybody who can do that for us, I'm listening.
Yeah, great, Gordon.
Yeah, I mean, obviously we do make lasers and photonic integrated circuits to that end, and do some of the control and packaging and so forth. I think obvious partners for us are sitting right next to me here. Obviously, Cold Quanta brings the physics to the table in the quantum sense for clocks and sensors. That's a perfect match. While we do some control work, it's not really our bread and butter, whereas the experts are sitting right next to me here. So working with Vescent on control of our photonic integrated circuits is absolutely something that we're wanting to do and to collaborate on. I can't help but imagine, although we haven't talked in great detail, that some of our high power amplifier technology might be useful to guys working in the fiber laser world and you know, in some of the other pumped laser applications. So that's another place we need to do some more talking.
Great, Scott.
I personally like collaborating because I'm a bit of a people person and I like smart, ambitious, entrepreneurial folks. But you know, when it comes down to your business decision of whether you collaborate or not, it's a trade-off between how much of the pie do you want to try to grab versus sort of time to market. And I do see in this space that time to market is key. There are some big technical challenges out there, and I think the folks that crack it first or in that first tier are going to win. They're going to be in a good position, and by partnering with folks, not reinventing the wheel, that makes sense. And we do a lot of partnerships. It is, I don't know, is that enough of an answer?
Yeah, that's enough. So Mark, before you answer, you actually just acquired a partner, didn't you?
We did, yeah. So announced thing. I'm back and live again. Right. So they finally want to hear what I have to say. So yeah, we're excited to announce the acquisition of Azurelight this week. So that'll become Toptica Photonics SAS.
So
and
what does Azurelight do?
Yeah, so they provide CW fiber lasers as well.
Oh.
So and
I'm proud that you've seen the light back.
We're always looking for ways to fill gaps in our offering, and when you look at the combination of what we can do with quiet, stable lasers combined with their ability to drive amplification, we can give you photons and performance. So when you look at something like our T-Rack solution, we want to make sure that we fill as many holes in that as we can to get to the physics package. Perfect. So we want to continue to drive that. I mean, at some point or another, most of us at this stage have talked or collaborated on projects. We can also gain access to markets with each other. So some of us play in different markets better than others. And we each bring a different expertise, but ultimately I think we're doing that where we can. Again, my push is, again, to keep collaboration open globally and focus on the area of expertise. Focus on the physics package to solve problems. And then we'll come behind with the right solutions for you, like we've been doing.
Great. And Sasha, you were just acquired by a partner, which is about to close, right?
It's subject to regulatory approvals, yes. I think it's an interesting industry in which we are in. On one side, we have large companies like Coherent, right? And then we have small, mid-sized companies across the entire value chain. So collaboration takes place, in my mind, in various ways. That's collaborating in creating confidence to the market to say, yes, we are here. We are going to make this happen together. Collaboration is all about, in my opinion, also about talents. I heard recently at another event that it's a talent-limited market. So in order to scale this, to make this happen, we need more talents. So I think it's our common responsibility to develop people, to develop know-how, to share know-how, to create the confidence out there. To say, yes, from a laser, component, system, integration point of view, software, all this is there to make it happen. So I think it's a common responsibility of all of us.
Great, thank you. Marco?
Well, it's a relatively complex answer. I mean, as a large company, we have exchanged with a lot of other laser companies because of components we make, from diodes to crystals to fibers. Then from a point of view of going to the specific of, among the panelists here, for example, I would love if Chris or Scott would come to me and say, we are building 1 million of quantum sensors and we need the diodes. Can you provide the diodes for that? I would love that. I mentioned before that I think that photonic integration will play a role in quantum devices, a strong role, and I think that the type of photonic integration is going to be different from what is used in telecom, because it will rely on visible wavelengths. So for example, will not be necessarily based on silicon photonics, but will be, for example, on platform like silicon nitride or indium phosphide. So certainly we would be interested in collaborations on that front.
Great.
I hope
great.
this answers your question.
Yes. Does anybody want to ask a question in the audience? Please. One or two?
Awesome.
Sure.
Hey, good afternoon. My name is Anjali Singh. I'm Vice President of Payload at a company called Planet. We're just down the street here. And we image the Earth every day and publish this imagery by, through a subscription service. And I can clearly see how quantum sensing, quantum computing, and all these other, quantum, I guess where the niche could be for this. So it's more really a comment, reach out, anjali.singh@planet.com. Let's talk. Let's see, if there's a value proposition that we can come up with. We operate these really tiny satellites that can be used for maturing some of these technologies. So encourage you all to reach out.
Anybody want to comment on that?
I didn't hear all the details.
Check, check.
Check.
There's certainly a number of ways that you can look at that. Scott mentioned earlier that their group is already doing, and so there's applications for that already. But not just looking at quantum, there's communication between those satellites as well, right? Whether it's ground to satellite or satellite to satellite. There's activity that we're involved with that we continue to drive that. So we're happy to help support that, and it all fits into the further commercialization of all of these technologies.
I'll just throw something out there. One of the applications is sensor fusion. Having precise position and timing information between multiple platforms and multiple sensors can open up new possibilities. A space-based company that does imaging, there could be interest there.
Mm-hmm. Okay, great. Anybody else? Are good?
In terms of space qualification of parts, it's well known that cost on the gallium arsenide work, very well under radiation. So we have done some radiation testing on our PICs and lasers. These can be used for everything from, QKD type format transmitters to the high power amplifiers for free space communication. And of course, they also belong in clocks and inertial navigation sensors.
Yeah, and I would almost turn the question around a little bit and say, bring us your requirements, especially for a clock, right? Whether it's ground-based timing or satellite-to-satellite timing, or how far are you looking to go beyond the clocks that are already in space and qualified? Do you need one more order of magnitude performance, 2 or 5? I doubt it's 5, but so we need to know the requirements there, because that helps us make sure that we're developing the right thing.
So actually, we work very iteratively, right? So we work with what are the capabilities out there. Let's field it. Let's look at what we can get, and then work the requirements iteratively. So we can start with something small, and then scale up, right? So we're not like one of the DoD companies where we work with very strict requirements. So it's really an opportunity to, to work something out.
Okay. All right, I want to give a quick snapshot here to upcoming events. At the end of February, we're going to have a quantum marketplace back to our normal Zoom format. It's public. We're going to run quantum networking testbeds, which is actually a very hot topic. All these companies are involved either with building these things, providing tools for these things, software, modeling, actually a company working on software-defined networking for the quantum stack, and then IonQ with their needs for quantum networking for scaling quantum computing. We don't have the full cohort yet, but we're also looking at doing network security post-quantum in late March.